In the previous video, I introduced a characterization of flat Earth through the notion of drop. Specifically, I said that a surface is flat if all observers or objects on that surface are in a zero-drop relationship with all the other observers on that surface, as represented by this diagram. I noted that it seemed likely that this zero-drop relationship was a necessary condition for a flat surface, but it was not sufficient. This means that even if we established the diagram as true, it would only be indicative that the Earth might be flat. However, such a property can be used to definitively establish that the Earth is not flat, and that is what I'm going to explore in this video. In the previous video, the zero-drop property was used with observers that were observing other observers on the surface. In this video, all our observers will be observing the same object, namely the Sun. The observations of the Sun involve taking two measurements: the azimuth, the direction I have to face to see the Sun, and the elevation, how far do I have to look up to see the Sun. As always, do not look directly at the Sun. It's very bad for you. In this analysis, we will be taking the measurements of the Sun at solar noon. Solar noon occurs when the Sun is at its highest point during that day, and it occurs along the same azimuthal direction every day. Therefore, we are primarily interested in the elevation measurement. We find that for many places on the Earth's surface, the elevation changes throughout the year, and that change takes place between two extremes. These extremes occur on the days we call solstices, which are in June and December. Many places experience solar noon at the same instance, and these all lie on the same azimuthal line. If we collect the data regarding the elevation of solar noon at places all over the Earth's surface, we find something interesting: that the difference between the angle of elevation on each of the solstices is a constant. This occurs everywhere one is able to view the Sun on both solstices during the year. Note that if on one of the solstices you can't see the Sun, this makes the notion that the difference is always a constant undetermined, not false. This constant value is 46.8 degrees. We can use this constant value with our zero-drop relationship to explore the idea of a flat Earth. Since I'm going to be doing the analysis by pen and paper, rather than complicate things trying to measure 46.8, I will instead be using the 45-degree angles of this set square. I can do this because of the fact that the elevation difference is a constant, and that's what's important, not its actual value, and because I do not intend making any detail measurements from the diagrams to compare with reality. So, where do we start? Let's put a line representing the zero-drop relationship in the azimuthal direction of the solar noons at a particular instance in time. On a flat Earth, all our observers of a solar noon at that instance should be along this line. How should we start positioning observers along this zero-drop line? We know that on some places on the surface, the solar noon elevation is always in the same direction, regardless of time of year. North of the Tropic of Cancer, that direction is south, and south of the Tropic of Capricorn, that direction is north. So let's start by placing an observer, A, on the left, representing the northerly observer, and drawing the elevations for the solstices in a rightward direction. Next, on the right, let's place the southerly observer, B, and draw in the elevations for the solstices in a leftward direction. First thing to notice is that at this stage the Sun is projected to be at different heights on the solstices, and that at point A the distance to the Sun on the June solstice is much smaller than the distance on the December solstice, meaning it should appear noticeably smaller in December. The converse is true for point B. In the event that this analysis of the zero-drop property shows that the Earth may be flat, these predictions are something that could be used to assist in further validating the flat Earth. What next? Well, let's consider an observer halfway between A and B. We place the point of our set square on the zero-drop line in the general direction of the suns derived from A and B. Immediately there is a problem. the edges of the set square don't meet up with the positions of the sun derived from A and B. If we move the set square to make it intersect with the sun positions on the solstices, we see that the observer is pushed not just off the zero drop line, but in fact off the graph paper completely. Already we have diverged from the necessary conditions for a flat Earth. But let's investigate some more to see how other observers would fare. If we consider other positions between A and B, we find that they are always to be found below the zero drop line, within the limits of our drawing, and that other observers have to be above the zero drop line to satisfy the condition that they are all observing the same sun. That means the only two observers in this diagram that are in a zero drop relationship with each other are A and B, but this is a relationship that we hypothesized, not constructed. This strongly implies that none of our observers are in a zero drop relationship with each other, the very opposite of the property needed for a flat Earth. Of course, this is but one attempt at examining our elevation data, and perhaps there exists a way to draw our observers following this schema to satisfy the zero drop property, but from what we've seen, that is unlikely. But it's not impossible. There is, in fact, a different schema that we can use that would allow us to have all our observers in a zero drop relationship, and that is demonstrated here. In this schema, the sun is considered to be at an infinite distance away, which in practical terms probably means it is a long way away relative to the objects being drawn. This is something that is always resisted by flat Earth apologists. Also, this schema makes predictions about the elevation angles. For example, that all observers measure the same angle of elevation regardless of where they are on the zero drop line. I only need to refer back to an earlier video to show that this is not the case, and that actual observers on the surface of the Earth measure different elevation angles for simultaneously occurring solar noons. So, where does this leave flat Earth apologists? Well, they could try and play around with the first schema to see if there exists an actual solution that allows all the observers to be on the zero drop line, bearing in mind that this would not be a definitive proof since the property is necessary but not sufficient. If they try this, they should also consider that a formal mathematical proof may be forthcoming that shows it's impossible to satisfy the zero drop property for observers with this constant angle between solstice measurements, in which case the game is over.